Okay. All right. So in this particular ratio problem, we have a car that accelerates uniformly from us and it covers some distance d after some time t. And this is determine the ratio that it takes to cover the first half of the distance compared to that second half of the distance. Okay. So our goal here is to find what the question mark is, so what that coefficient is, in order to make the statement true. So here visually, there's a car on the top. It starts at 0. And here's your acceleration, and it says acceleration is uniformly, meaning it's the same in both scenarios. So really the top and the bottom diagram is essentially the same. Okay. The only thing we got to find is how much time did it take to cover the first half of the distance here relative to the second half of the distance. So as the car accelerates, the time that it takes to cover the first half is different than the time that it takes to cover the second half of the distance. All right, so let's find that coefficient. So to do so, I'm just going to go ahead and help you visualize here. So here is 0 meters, and then or 0 whatever unit, and this is to some distance d over 2. Right. So in the top diagram, the whole length is d. So d over 2 here is half. I don't know how much time it takes to cover this first half. I'll just call it t1. So while the ratio denotes t from 0 to d over 2, that statement on the left, I'll just call that t1 because it is the time it takes to go from 0 to d over 2. And likewise with the second half of the distance here, that's d over 2. This will be d, and I'm just going to call the second time t2. Okay, so equal distance, but it will take different time because the car is speeding up. So let's go ahead and do it. In order to do this one, I'm just going to go ahead and use my displacement function only because this particular problem involves it involves time, and it involves distance. Okay, so I'm going to go ahead and use this function because it has delta x, and it has an a and a t. While there is a VIT term, this particular problem starts at rest, so that'll be easy to cancel out. All right, so I'm going to go ahead and set up my usual grid here. So I'm going to go ahead and actually solve for t1, which is the time it takes from the starting point to where it is halfway or half the distance. Okay, and then on the right side, I'm actually going to solve for I'm going to make a comparison for the whole entire time. Here's why. Well, if I can find t1, well, I know the total time is t, so to find t2, I can find t2 by taking the total time and subtracting from the first segment. Okay, so there's a reason why I'm setting up t1 and t. So you notice here I'm not touching t2 till later, because if I know t1, I can solve t2. All right, so therefore I'm just going to go ahead and set up my displacement function here. Generically, it is delta x equals VIT plus 1/2 AT squared. Start canceling stuff out that's relevant. So here, the diagram sets 0, the wording says it starts at rest, so I'm just going to cancel that out. And likewise on the right side, I want to go ahead and cancel out the VIT term. Okay, and from here, just go with what's presented to you, right? So for t1, well, what can you replace delta x with? Well, delta x in this particular segment is from 0 to d over 2. So my delta x here could just be swap out for d over 2 because that's a true statement. The rest of the statement on the right, I'm just going to go ahead and keep it as is. However, you notice here, generically it's just t squared, but I have chosen to use the subscript 1 to indicate the time that it takes to cover the first half of the distance. So I'll just call that t1. So really, it's the same thing. I'm just going to call that t1. You can call it ta, tb, whatever you want, but I would just encourage you to go from left to right, depending on the diagram. Okay. All right. So as you can see here, I can do the same on the for the total distance. So if you look at the very top, it states that the car travels some distance and some time, which are not given quantity. It's all in variable form here. So what is my delta x? It's just d, the total distance covered. Well, what's my t? I'm just actually going to leave this as t because in the diagram, the total t is just t. Okay, so I'm not going to use a 1 or a 2 here because t1 is for the first segment, t2 is for the second segment, but the total time is just t by itself with no subscript. So I'm just going to go ahead and use the information presented in the wording and in the diagram. So I have d here, the total distance is equal to 1/2 times the accelerations times whatever t is square, and this t once again is the total time. Well, as you can see on the left side, the halves here you can cancel out. There's a 2 on the bottom, and there's a 2 on the bottom here, so that'll cancel out. So really you have d is equal to a times t1 squared. Well, you notice in both these statements you have a d isolated, so you have d is equal to a t1 squared. On the right side here you have d is equal to 1/2 a t squared. So I'm just going to go ahead and substitute out d on the right side, or you can go from left to right, right to left. I'm just going to go ahead and go from left to right here. So I'm going to swap out d. So instead of saying d, I can replace it with a true statement or expression here. I will say d is equal to a times whatever t1 is squared. On the right side, nothing has changed, right? So if you notice here, both sides has an a, so I'm just going to go ahead and cancel out a. So here we have t1 squared is equal to 1/2 t squared, t being, again, the time of the total, the time to cover the whole entire distance d, okay? So to solve for t1 here, I'm just going to go ahead and square root everything, all right? So to get t1 by itself, you take the square root on the left side, you also take the square root on the right side. So the square on the left side leaves you just with t1. The square root of t squared here just leaves you with t. And then the square root of the 2 on the bottom would just be radical 2. So from here, you can just simplify it into a fraction if you like, or into a decimal if you like. So really it's just 1 divided by radical 2. So if you do that on your calculator, 1 divided by radical 2, you'll get 0.707 t. Well, now that I know what t1 is, I can find t2 just using a little common sense. So I'll go ahead and replace t1 here with the statement that I just found. So t1 is about 0.707 of the total time. Well, if I know t1, then I can find t2. Well, the total time is t, so to find t2, I can just take t minus the first segment. Okay, so from here, you can just replace out t1. So t, once again, is the total time minus the time it takes to cover the first segment, which is about 0.707 of the total time. Well, here's 1t minus 0.707t. So basic math will leave you with about 0.293 t. So from here, we can just go ahead and plug it back into our expression. What is the time for the first half of the distance here, right? So from 0 to d over 2, which is t1, t1 is 0.707 t. That's what I did there. There's the question mark. I just carry that over. Well, how about the time that it takes to cover the second half of the distance, right? So while the expression here is t from d over 2 to d, in my work, I just call that t2. Why just solve t2? So t2 is simply 0.293 t. So both sides have with t, cancel that out. So in order to solve for the question mark, divide both sides by 0.293 to isolate for the question mark. So if you do that correctly, you'll get a value of 2.41. So that's our coefficient, okay? So that is the answer for this particular problem. And here's another one. So if you need to read this one. Here it says two bodies, starts at rest, they move in a straight line, they cover some distance d. But it says here, if the time taken by the second body to cover this distance is double the time taken by the first body, find the ratio of A1 to A2. So here's the diagram for you. Both vehicles cover a distance d. However, it did say that the time taken by scenario 2 is more. How much more? 2 times the t. So in the first scenario, whatever t is here, in the second scenario, it takes twice the time, hence the 2 coefficient. I drew the acceleration vector here for you differently for this one because using common sense, there's 2 ways to look at it, right? If you cover the same distance in less time, that would imply that you accelerate faster. Or the other perspective is, well, to cover the same distance and if you take more time, acceleration is less. So you notice here my acceleration vectors are drawn differently here in terms of magnitude. All right, so let's go and crack this one out. This one's not too bad. I'm going to go back to my displacement function because the question involves time, it involves a, it involves distance, right? So I'm just going to go ahead and do this for you, a1 and then a2, or scenario 1, scenario 2. For this particular problem, the a's are different, so I'll just reference what's different here, and that is your acceleration. Here, I'm going to start as usual, my displacement function. I'm going to cancel out vi. Once again, vi here says 0 because it says two bodies starts their motion from rest. So the initial velocity here is 0. So I'm going to do the same on the right side. I'll cancel out what is insignificant or what's not important. Well, on the left side, I can replace delta x with d because the problem sets that in both scenarios, the distance traveled stays the same, d and d. Okay, so for this one, instead of a, I actually call that a1 because what's different about this scenario? Well, it's the acceleration and the time. Well, here t remains t. I didn't add any subscripts here for t because in the diagram it's just call it t, and on the bottom it just calls it 2t. That's entirely up to you. If you want, you can call this t1, you can call this t2, and you can say that t2 is 2t1. But I'm just going to call it t and 2t. Why not? Okay. So once again, the t doesn't have a subscript because that's what I've chosen. It's entirely up to you when you do these practice problems. On the right side, Well, what's delta x? It's also d, because the one thing that's consistent in this particular problem is the distance covered. Okay, the 1/2, it's carried over. And what's my a here? Well, unlike the other problems you've seen, a here is a2 because the acceleration are different for these two scenarios. What is t here? Well, t in the second scenario is 2t because I highlighted for you here. Right? It says it takes double the amount of time. So instead of t generically here, you would just replace that statement with 2t in parentheses. And once you do that, you distribute the exponent 2 to the 2, which makes it 4. And then t squared is just t squared. So if you're keeping up right now, on the left side, everything stays the same. And I can substitute that in for d. So if you've seen the first video and you know what I did there in terms of strategy, I'll solve for things that are the same, and then I'll just substitute it out. So instead of saying d on the left side, I'm just going to say it's 1/2 a1t squared. So on the left side here, it's 1/2 a1t squared. On the right side, I just distribute the exponent 2, so I'll get a coefficient of 4 here. And then I'm just going to clean up a little bit. Okay, there's a 1/2 that cancels out with the 1/2 on the right side. And there's also a t squared. This is also a t squared, so I'm going to cancel it out. So really at the end of the day, if you clean it up, it says a1 is 4 times the acceleration of a2, which makes sense because we established earlier using common sense that to cover the same distance in less time, you need to accelerate faster. How much faster? 4 times faster. So to do this ratio, a1 is 4 times as big. So to make sure you express this ratio correctly, you would say the ratio is 4 to 1. It's 4 to 1 because a1 is 4 times greater. So if a2 is 1, 1 times 4 is 4. Okay, so make sure you express this ratio correctly. It's 4 to 1, not 1 to 4, based on the notation presented in the problem. And that's it. All right, stay nerdy, don't be wired.